finish up chapter 20 here with the cardiac cycle. So this cardiac cycle here, just to back up a little bit. So the heart essentially is two pumps that work together. So the right and the left half, each pump has a primer, which is the atrium. Again, we have that quick action potential, and then the slower kind of power pump is the ventricle with that extended plateau portion that allows that extended contraction. So this cardiac cycle is a repetitive pumping process that begins with the onset of contraction and ends with the beginning of the next contraction. So that makes one complete cardiac cycle. So we have systole and diastole. Systole is the contraction of a chamber. Diastole is relaxation of the chamber. So contraction versus relaxation. And blood moves through the circulatory system from areas of higher to lower pressure. So it's changes in pressure that are really driving this. So if we look at the beginning of the cardiac cycle, so here the heart's relaxed. So we have passive ventricular filling. So the ventricles are filling up. So again, as we looked at earlier, before the contraction begins, all the chambers are relaxed. So at rest, most of the blood movement is into the chambers. It's passive, just resulting from greater blood pressure in the veins than in the heart chamber. So it's driving it again, always going from high to low pressure. So there's a lot of pressure in the veins, smaller diameter pushes it into the atria. So as blood moves into the atria, much of it flows into the ventricles for two reasons. One, the AV valves are open. So again, here's our valves. Here we have our tricuspid and bicuspid, they're open. And that atrial pressure is slightly greater than the ventricular. So again, we have more pressure here in the atria than the ventricles. So it goes from high to low. So the valves are open and we're moving from a high to low pressure. And this is a passive ventricular filling. So then we move into atrial systole, which again is contraction. So this is active ventricular filling. So the SA node generates that spontaneous action potential to stimulate contraction of the atria. So remember, that's the P wave of that ECG that we finished up in the last video. The atrial contraction begins the cardiac cycle. So as they contract, they carry out the primer pump function by forcing more blood into the ventricles. So there's already some flowing in, but as they contract, again, our little gray waves here indicating the contraction, it forces more of the blood into the ventricles. Then we have ventricle systole. So we have contraction of the atria first, then contraction of the ventricles. Again, slower action potentials moving through there, fewer gap junctions. We get that contraction more at the base, at the apex of the heart. So those action potentials pass to the AV node down those bundles, and the Purkinje stimulating that ventricular contraction or systole. So this activity is that QRS complex of that ECG that we looked at the end of the last video. So as the ventricles contract, that pressure increases, and that causes the blood flow toward the atria, and it closes the AV valve, because again, we want one-way flow. We don't want the blood that is in the ventricles to be moving back into the atria. We don't want that to happen. So whenever we get that ventricle systole, what's going to happen are these atrial valves, the tricuspid and bicuspid, are going to close, and that's going to prevent that blood from flowing back into the atria. So now we get the period of ejection. So the ventricular contraction continues. Again, we get that plateau phase. So that pressure continues to build until it overcomes the pressures of the pulmonary trunk and the aorta. Okay, so again, here on the right ventricle, as that pressure, as the contraction continues and our pressure builds up, eventually it becomes higher than the pressure in the pulmonary trunk, and it opens that semilunar valve. Same thing on the left side. So that left ventricle stays contracted. Eventually enough pressure occurs to allow the opening of that semilunar valve in the aorta, but that can only happen after the pressure in the ventricles is greater than the pressure in the aorta or the pulmonary trunk. Then we get the ventricle diastole. So again, this is relaxation. So it's called isovolumetric relaxation. So during that ventricular repolarization, which is the T wave on the ECG, that leads to the relaxation, the diastole. So as that begins, the ventricles relax. That causes the pressure to decrease below what is in the pulmonary trunk or in the aortic arch. And so consequently, the blood begins to flow back toward the ventricles. Again, we don't want that though. We want one-way flow. But as the blood starts to come, as the blood starts to come back in, as the pressure changes, as it decreases, and the blood starts to come back in, that's going to close those semilunar valves so that the blood can't go back into the ventricles. Right, so if we look at our complete, again, it's pretty small here whenever it's all together, but that complete cardiac cycle. So again, we have the complete heart relaxation. The cycle begins with atrial systole or contraction that actively forces blood into the ventricles. Then we get ventricle systole or contraction. That's going to increase the pressure in the ventricles. It's going to close the tricuspid and bicuspid valves to prevent flow back into the atria as pressure continues. So as we get continued contraction, more pressure build up here in the ventricles. That's going to force the blood out into the aorta or the pulmonary arteries. Then we're going to get that pressure continues. Then as the pressure starts to drop in the ventricles, that's going to close those semilunar valves so that the blood doesn't go back into the ventricles. And then we get our complete relaxation. Excuse me. So that atrial systole and active ventricular filling. So again, depolarization of the SA node generates the action potentials that spreads through the atria. That's that P wave of the ECG, and the atria contract. That completes the ventricular filling. So there's some passive at the beginning, but we get this complete active filling. Then at rest, the contraction of the atria is not necessary for the heart to function. During exercise, though, atrial contraction is necessary to function, so the heart can pump more, 300 to 400 times more or percent more blood than at rest. Now in ventricle systole, so again, that QRS complex, the ventricles start to contract. We get that increase in pressure in the ventricles, causes those AV valves to close and starts the contraction of the ventricles. Those semilunar valves that were closed in the previous diastole continue to be closed. And just kind of some numbers here, about 120 to 300 milliliters of blood are going to fill the ventricles. And then that's left from the last diastole when the atria emptied. So this is called the end diastolic volume. We also have this period of ejection, so that pressure in the ventricles is increased. So now it's greater than the pressure in the pulmonary trunk and the aorta. That pushes the cusp of the semilunar valves to opening them, and the blood is ejected from the ventricles. So the pressure in the two ventricles is a little different. It's 120 millimeters. In the left ventricle, only 25 in the right. So remember, blood in the left must be pumped to the whole body. In the right, it's only going to the lungs. So it doesn't need quite as much force or pressure. So then after that initial spurt, the pressure starts to drop. And then we have this end of the period of ejection, and that's called the end systolic volume. So still a little bit of blood remaining in the heart. So then the ventricular diastole, this isovolumetric relaxation, so completion of the T wave results in the ventricular repolarization and relaxation. The pressure is falling rapidly. So now the pressure is higher in the pulmonary trunk and the aorta. And this elastic recoil of the arteries causes blood to flow back toward those ventricles, and it closes those semilunar valves. And again, note here that those AV valves are still closed as well. They have not yet opened. Then that ventricular filling that's passive, so while the ventricles are in systole, again, contraction, the atria are still filling with blood that's coming in through that passive transport from the veins to the atria. So as the pressure rises in the atria, above the ventricular pressure, that's going to open those AV valves. And then blood flows into the relaxed ventricles by that passive filling. Okay, so the events, again, just looking at this in another way, again, back to our kind of looking at the events. So the ECG here at the top, so again, the P wave, we have our QRS complex here. So again, this is just another visual way of looking at the cardiac events. So again, that active ventricular filling, the isovolumetric contraction, period of ejection, followed by relaxation, and then that passive filling. So again, just to kind of visualize what's happening, putting it all together, helping you to better understand what's going on. All right, now talking about the sounds of the heart. So we all know that the heart makes that lub-dub sound. So that first sound is that lub. That is caused by those atrial ventricular valves, or the AV valves, and the surrounding fluid vibrations as the valves close at the beginning of ventricular systole. So the lub is whenever we're getting the beginning contraction of the ventricles and those AV valves are closing. Then the dub sound, the second sound that we hear, that's from the closure of the aortic and pulmonary semilunar valves. So when the AV valves close, we get the lub. When the semilunar close, we get that dub, which is a little bit longer of a sound. And then occasionally we can actually have a third sound that occurs, and this is caused by turbulent blood flow into the ventricles that's detected near the end of the first about third of systole. And then there can be some abnormal heart sounds as well that are called heart murmurs. And then this is where we get incomplete valves that are closing, or valvular insufficiency. And this is where blood flows through backwards when the valve is closed, or it's regurgitation. So that turbulence causes a gurgling or swishing sound, and that is detected as a heart murmur. Then the stenosed valve have abnormally narrow openings, producing very turbulent blood flow, and that produces kind of a rushing sound before the heart sound whenever that happens. All right, and then kind of wrapping up here, talking about the mean arterial blood pressure, or the MAP. So this is slightly less than average blood pressure in the aorta. And it is measured by the cardiac output, which is CO, by that peripheral resistance, or PR. So the mean arterial pressure is calculated by multiplying the cardiac output and peripheral resistance. So what are those? So the cardiac output is the amount of blood pumped by the heart per minute. So how much blood can our heart pump every minute? Well, how do we calculate that? Well, that is calculated by multiplying the stroke volume by the heart rate. And the stroke volume is the blood pumped during each heartbeat. And then the heart rate is the number of times the heart beats every minute. So how much blood is being pumped with each beat times how frequently the heart is beating. That gives us our cardiac output. Now there is some cardiac reserve And that's the difference between the cardiac output at rest and the maximum cardiac output. So again, not all of the blood is leaving, so that kind of reserve is called cardiac reserve. All right, then the other part of our mean arterial pressure is the peripheral resistance. And this is the total resistance against which the blood is pumped. So how much resistance, how much force is needed, because there's a lot of resistance to that pumping. So there are multiple factors that can affect that mean arterial pressure. So first of all, looking at things that affect cardiac output. So again, this is stroke volume, the amount of blood, and heart rate. Both of those would impact cardiac output. So decreased blood pressure, decreased pH, increased carbon dioxide, decreased oxygen, low exercise, and even emotions. Those can all increase sympathetic stimulation, which decreases parasympathetic. That's going to increase our epinephrine, norepinephrine, that's our fight or flight. That's going to cause secretions of the renal medulla that increase the force of contraction, also increase the heart rate, both of which would increase cardiac output and therefore increase that mean arterial pressure. Now also, we can increase the amount of blood volume if we increase exercise or change from standing to lying. Those increase venous return. And that increase in venous return increases the force of contraction. So it ejects increased to that end diastolic volume. That's going to increase the stroke volume, again, how much blood is leaving the heart, which also increases cardiac output and increases the mean arterial pressure. Then the factors that can affect the peripheral resistance, decreased blood pressure, pH, carbon dioxide, and oxygen. Decreasing those can then cause increased constriction of the blood vessels. That increases the resistance. So if the blood vessels are smaller, it takes more force to pump them, because again, we're moving from high to low pressures. So if we have a lot of resistance, that increases the pressure, causing more resistance that increases that mean arterial pressure. All right, so then how do we regulate the heart? So that output must change to meet our demand. So if we're just sleeping or if we're exercising, we need to be able to regulate the heart. So there's intrinsic regulation and extrinsic regulation. Intrinsic is normal heart function. Extrinsic is whenever we get neuronal or hormonal control. So our intrinsic regulation, we have preload and afterload. So the preload is the amount of stretch of the ventricular walls. So the greater the stretch, which is the preload, the greater the force of contraction, which makes sense. So if we can stretch the ventricles, think about it as a balloon. If we stretch that balloon open more, then that means that we can get a greater force of contraction. We have more pressure, more force behind that. And that's known as the Starling's law of the heart. Now the afterload, this is the pressure of contracting ventricles must produce to overcome the pressure of the aorta and move the blood out. Because remember, we're going from high to low pressures. So in that cardiac cycle, what allows the blood to move from the ventricles to the aorta is that contraction of the ventricles that creates enough pressure to push the blood out into the aorta or the pulmonary trunk. So that's referred to as the afterload, the pressure of those contracting ventricles to overcome and be higher than that of the aorta or pulmonary trunk. So the heart's not as sensitive to this as it is to changes in the preload. So typically, the stretching of the ventricular walls is more a factor than the afterload. Now, if we look at the extrinsic regulation, now again, neuronal or hormonal control. So we're back to our nervous system. So our rest or digest, parasympathetic, fight or flight, sympathetic stimulation. So with the parasympathetic, this is supplied by that vagus nerve, one of those cranial nerves So this decreases the heart rate. Again, rest or digest for slowing things down. Acetylcholine is secreted and hyperpolarizes the heart, meaning it's harder for an action potential to get started to cause contraction. Now, with sympathetic stimulation, this is supplied by cardiac nerves that innervate the SA and AV nodes, also the coronary vessels and the myocardium. So this increases the heart rate and the force of contraction. So epinephrine and norepinephrine get released for this. And then that increased heartbeat increases the cardiac output. And increased force of contraction causes a lower end systolic volume. So we're emptying the heart at a greater extent. So we're forcing more of the blood out. But the limitations of this is that the heart doesn't have as much time to fill. And then just the hormonal control of that. So that epinephrine or norepinephrine from the adrenal medulla, this occurs in response to physical activity. Also emotional excitement, as well as stress. Now this takes longer than sympathetic stimulation, but it lasts longer. So it takes longer to get there, but once it's there, it causes a longer effect.